Everybody labeled them this way? Bing.
So on the one on the right, so the arrow on the top is going to be longer than the arrows on the bottom, because they're, well,
Yeah, so yeah, we'll get there in a little bit, but the arrow on pointing up is going to be equal to the sum of the two pointing down. Yeah, I should have drawn it a little longer. Well, we'll get to that more in a little bit. Right now we're focusing on forces. Okay, so everyone says they labeled them the same way as I did. What else? How else could you have labeled something? Anybody call this downward force here the weight of the upper block? This one.
I said force of the lower block.
You called it the force on what force on the lower block? That's okay. Nobody called that the weight of the upper block? You did, yeah. So you want to jump to that step, right? Because what is this force going to be equal to? It's going to be equal to the weight of the upper block. But I don't want you to do that yet, because it's really, when you write weight, you're talking about an interaction between the Earth and an object. Right? These two blocks, there is a tiny gravitational attraction between those two blocks, right? But it's small. It's so small we can ignore it. In a few chapters, we'll have the capability of calculating the gravitational force between those two blocks. It's a teensy tiny little force. We would never be able to notice it with all these other forces acting on it, okay? The gravitational force, the weight of the object, is between that object and the Earth. So you don't want to indicate that here. You want to indicate it as just those two things are touching each other, they're pressing on each other. And then we'll have the tools pretty soon to look at this and say, well, what is this? What is this force? NLU, right? Normal force on the lower from the upper. How can I figure out what that is? And what we're going to do, we're going to link it to a force on the other one. Because somebody brought up earlier, when object A pushes on the ground pushes back on object A, right? And those two forces have to be equal. When two objects interact with each other, they always interact with equal and opposite forces. So when the lower block pushes up, that's this one here. When the lower block pushes up on the upper block pushes down on the lower block, that's this one over here. And those two forces have to be equal in magnitude and opposite in direction. When two things interact with each other, they always interact with equal and opposite forces. And those are an interaction between those two objects, the upper and the lower block. That's Newton's third law. We're kind of jumping around, hitting them out of order. Newton's third law is that when two objects interact with each other, they interact with equal and opposite forces. So that helps us now. When you look at the free body diagram, try to get in the habit of just drawing the actual force. This is the upper block pushing on the lower block. Then we can look at the free body diagram for the upper block and say, oh, wait a minute. These two have to be the same. The two with the red X's have to be the same magnitude. And what is the magnitude of the one over here on the upper block with the red X? That has to equal the weight of the upper block because it's not accelerating. It's just sitting there. Now we've linked it back and we can say this is equal to the weight of the upper block. But that's not always the case. Sometimes these blocks are accelerating and it's not always the weight of the upper block. So I just want you to get in the habit of kind of walking through it in full detail like we're doing here, because as soon as we start changing, as soon as we put this on an incline instead of a flat surface, or as soon as there's some acceleration or a pulley attached to something, it doesn't have to be the weight of the other block. It's a component of the weight, okay? So it's better to sort of keep the forces separate and then work through and link them after you draw your free body diagram. Okay, so what do we call these two with the red X's? We call those a Newton's pair. Newton's third law pair. Those are, so any two objects that are interacting interact with equal and opposite forces. Do you ever have a Newton's pair in one free body diagram? The answer is no, and the reason is that a free body diagram has all the forces acting on that object. So that free body diagram is all the forces acting on the lower block. So a Newton's pair is a force acting on the lower block due to the upper block, and a force acting on the upper block due to the lower block, right? Those are two different objects the forces are being exerted on. So they would have to be in two different free body diagrams. So for example, students love to try to do this, to try to call those two a Newton's pair. The force of gravity is pulling the object down, and the surface is pushing it up, and those forces are equal, right? They're opposite, right? But they're not a Newton's pair because they don't come from the same interaction. They don't have to be equal. If this was in an elevator accelerating upward, the normal force would be bigger than the weight of gravity. Okay? A Newton's pair, they're always equal and opposite. It doesn't matter if there's acceleration or not. So those two are not a Newton's pair. They always have to be in different free body diagrams, your Newton's pair, because the free body diagram is only the forces on that object, and a Newton's pair, the forces are on the two different objects, right, due to the other one. Okay? They have to come from the same interaction. All right, so let's see if we can do this. Just a quick check on free body diagrams. We're throwing a ball The ball is right there. At the top of its trajectory, as it's heading toward its target. Okay, a baseball heading towards home plate. It's at the top of its trajectory. And we want to know, what does the free body diagram look like at the instant and we're going to do it a couple of ways. One, we're going to ignore air drag. And then we'll include it. Yeah, what's my rule of thumb for drawing these free body diagrams? What's touching the object? Air, but we're ignoring the effect of air, right? For this first part. So nothing is touching it. And what can reach in from a distance? Gravity. So that's it. Okay? That's it. What else is exerting a force on it? It's moving. Yeah, I give you that. It's moving, but nothing is, it's moving under its own, inertia. We'll talk about that next time. It's, once something starts moving, it's going to keep moving on its own. It doesn't need a force to keep it moving. It only needs forces to change its motion. So to get that ball moving, somebody had to apply a force to it, right? And to stop it, the ground is going to have to apply a force to it, right? But to just have it move through the air, it doesn't need a force to move. Okay?